All right, Matthew, here we go. We've got 9-8, factoring completely. I think this is going to be our last lesson in factoring. So what does it mean to factor something completely? Factoring completely, and we kind of touched on it on the last video, means that we can't stop factoring until everything is prime. So if something can still factor, we're not done. Sometimes that means we might have to factor twice in a problem, 3 times, even 4 times. We just can't stop factoring until we're done. So how do we decide how we're going to keep on doing this? Well, we got a little decision tree that we're going to make. Kind of like questions to ask yourself as you're going through a problem. The first question you need to ask yourself is, how many terms, or no, is there a GCF? That's the second question. Is there a GCF in the problem that I'm looking for? So this problem right here, yeah, that has a GCF. So if you have a GCF, you always want to do that first. So this one would factor into x times x minus 5. Now, whether or not you found a GCF, you need to keep moving down this decision tree. So after you've asked yourself if there is a GCF, the next thing you have to ask yourself is how many terms are you looking at? So are you looking at a binomial or are you looking at a trinomial? In this case, we would have been looking at a binomial right here. So maybe we weren't sure if we were done factoring. So we would have said, okay, how many terms do I have? Well, it's a binomial. Okay, so let's go over what do we do when there's 2 terms. When we have 2 terms, we look for the difference of 2 squares. So I'd ask myself, is this the difference of 2 squares? Well, it's the difference, but those aren't squares. So then I would know, oh, I'm done, because nothing else factors. The x isn't going to factor, obviously. And then x minus 5 isn't the difference of 2 squares. So that means I'm done. I've factored as far as I can go. X is prime, x minus 5 is prime. Sweet, done. Okay, sometimes you won't be done. So if you are going down this decision tree and you're asking yourself how many terms you are, when you have 2 terms, you're going to look for the difference of squares. Remember, the difference of 2 squares method is when we have this one is the perfect square of x and this one's the perfect square of 5y. When we do the difference of 2 squares, we would factor this into x plus 5y, x minus 5y. All right, what if the problem we were looking at had 3 terms? Well, when we have 3 terms, there were 2 different methods we looked at. Is there a leading coefficient is the question we have to ask ourselves. Leading coefficient, that just means with the leading term, the first term in the trinomial, is there a number that's going with the variable? The first thing that we did was problems where that was a no. I think that was back in like 9-5 or so. So that was problems where it was x squared plus bx plus c. And we had a method for this one. We said in this type of problem, we would do a little t-chart for 15. And 15 is 1 and 15, 1 and 15, 3 and 5. And then we would ask ourselves, do any of those pairs of factors add to give us 8? And yeah, 3 and 5 do. So this would factor into x plus 3 and x plus 5. So that's how we would factor it when there's no leading coefficient. And then back in lesson 9-7, I think, we turned into problems where we did have a leading coefficient. We did the guess and check method. Horrible name, but pretty cool method. So yes, that's when we have a number out front like this problem here. Remember, on these types of problems, we did a t-chart for the number in the back, which is 5. That can only be 1 and 5. And then we did a t-chart for the number in front, which is 2. So that can only be 1 and 2. And we said after we did these t-charts, we would set up 2 parentheses. So the leading coefficient is 2, and the leading term is 2x squared. So that means since there's only one combination that gives us 2, that first term has to be made from 1x and 2x, because x times 2x makes 2x squared. And then we just have to find the combination that works for the last term. So we could put a 1 here and a 5 here, or a 5 here and a 1 here. Well, our first combination is the one that works, where we have a 1 here and a 5 here, because what we're looking for is to multiply these inner terms here and get 2x, and then multiply these outer terms here and get 5x. And what we want to see is after we've done that multiplication, we want to see if those two together give us our middle term, and they do. 2x and 5x gives us 7x, so now we know that we've multiplied it or factored it correctly. So that was the guess and check method. Now, when you're done with any of these terms, you need to ask yourself, can you factor again? So after you've done these problems, you need to look at what you're left with. So I'm left with x plus 1 and 2x plus 5, and say, am I actually done? Well, to figure out if you're done, you go all the way back up to the top and start asking yourself, is there a GCF? How many terms do you have? So right here, I have 2 terms. So then I'd go over here and say, oh, I've got 2 terms. Is this the difference 2 squares? No, those are both positive. And those are both positive. I'm done now. So once you have eliminated all of your possibilities and you've gone as far as you can go and nothing's factoring, then you can finally say it's factored completely. So let's look at some of these problems of factoring completely, keeping in mind this decision tree as we go through it. So I'm going to be referencing this as we go through these problems. All right, so here's the first problem. Factor 2x squared minus 10x plus minus 48. My first question always will be, is there a GCF? Does it have a GCF? Yeah, it does. 2 goes into 2, 10, and 48. So the first thing I'm going to do is factor out the GCF. So the GCF is 2, so that's going to leave me with x squared minus 5x minus 24. All right, you might think you're done, but you're not. The next thing you're going to ask yourself is, how many terms am I looking at? Well, we're not going to look at the monomial. We're going to look over here. So I've got 3 terms. That's a trinomial. So trinomial, 3 terms. Okay, I'm going this direction this time. All right, what do I look for 3 terms? Is there a leading coefficient? So over here, is there a leading coefficient? No, there's no number in front of x squared. We're not talking about this factor. We're just talking about the trinomial here. There's no leading coefficient. So what do? No leading coefficient? What am I going to do now? Magic factoring decision tree. Okay, so this is the one where I would do x squared plus bx plus c, where I just do the 1t chart. So I'm going to do a t chart over here for negative 24. Now, since that's a negative 24, and then this is a negative 5, one of my numbers is positive and one of my numbers is negative. And it looks like the bigger number is going to be negative because this middle number is negative. So I'm going to think of positive 1 and negative 24. Does that add to give me negative 5? No. Let's move on. 2 and negative 12. That gives me negative 10. I'm getting closer to the answer, but not quite there. Let's try 3. Positive 3 and negative 8. Does that give me negative 5? Yes, it does. So you have to remember to keep the factor that you did earlier. And then the trinomial splits up into x plus 3, x minus 8. All right, so we just did that. Are we done? No. What we're going to do now is follow the arrow down, and it says, can I factor again? So I'm talking about these 2 binomials that I have. Are they factorable? Well, I would start back up here at the top and say, is there GCF? No, there's no GCFs on either one of those. How many terms are we looking at? Well, these both have 2 terms. So let's go over to 2 terms. Are these the difference of 2 squares? That's a difference, but they're not squares. And these aren't squares. So it doesn't look like any other method works. Now I know I'm done. I have factored completely. 2's prime, x plus 3's prime, x minus 8's prime. Let's do that one more time. Starting on number 2, is there a GCF? Yes, there is. I've got a y on both of these, so I'm going to factor out a y. What am I left with? I'm left with x squared minus 1. All right, what should I do next? Decision tree tells me to look for how many terms. I've got 2 terms right here. Okay, 2 terms is over here. All right, what should I look for in 2 terms? I should look for the difference of 2 squares. All right, is this the difference of 2 squares? Yep, this is the perfect square of x. That's the perfect square of 1. So this factors into x plus 1, x minus 1. And the y stays out there. So this one factored into x plus 1, x minus 1. The y stays out. And then we'd get to the bottom here and say, can I factor again? So I'd come up, do I have a GCF? No. How many terms do I have? There's 2 terms for these. Are these the difference of 2 squares? No, they're not. So then I would know, okay, I'm finally done. All right, now let's look at a problem where we're going to have to do a lot of factoring. Okay, so we're going to leave the factoring tree behind for right now, the decision tree. We're going to try to remember all those steps that I'm supposed to look at. Step number 1, I'm going to ask myself, is there a GCF? Yeah, there is. If I'm looking at this, it looks like 3 goes into both of these numbers, and x does. So they both have an x. So I'm going to factor out a 3x. That leaves me with x to the 4th, and then 3 goes into 48 16 times. So x to the 4th minus 16. There's my first step. I asked myself, did I have a GCF? The answer was yes. Next step, how many terms do I have? There are 2. So what should I do when I look for 2 terms? I should look for the difference of 2 squares. Is this a perfect square? Yes, that's the perfect square of x squared. Is this a perfect square? Yes, that's a perfect square of 4. So I can factor this one again because it's the difference. So the 3x is going to stay out there. And then I'm going to do x squared plus 4, x squared minus 4. Are we done? No. The decision tree says, can I factor again? So I go to the very top of my paper and ask, do I have a GCF? No, I don't have GCFs there. Then I ask myself, how many terms? There's 2 terms on both of these. Then I ask myself, is this the difference of 2 squares? Well, these are both positive, so no for that one. One of these is positive, one of them is negative. So maybe, let's see, this is the perfect square of x, and this is a perfect square of 2, so it factors again. So the 3x is going to stay out here. X squared plus 4 stays out there because I factored it earlier. And then this last binomial here is going to factor into x plus 2, x minus 2. Now we're finally at the point where these won't factor again because these are not the difference of 2 squares. We're finally done. It factored 3 different times. All right, next one. Is there a GCF? No. Oh, that's different. There's not a GCF there. Okay. Well, how many terms are there? There's 3. So this is a trinomial. Is there a leading coefficient? Is there a number out front? No. So this is the type where I would do the t-chart. Okay, so both of these numbers have to be negative because this is positive, this is negative. So -1, -36, -2, -18, -3, and where am I at? -9, no, 12. -4 and -9. -6 and -6. All right, there's all my combinations. Do any of them give me -13? Yes, these 2. All right, so my first term is not x. My first term is x squared and x squared because that's how I'm getting this x to the 4th there. So it's going to be x squared minus 4, x squared minus 9. Okay, so we've made it through the first pass through our decision tree, and we have to ask ourselves, does it factor again? There's no GCFs. These are binomials, so we have to ask ourselves, are these the difference of two squares? And they both are. This one factors into x plus 2, x minus 2. And this one factors into x plus 3, x minus 3. And we have to ask ourselves, does it factor again? And in this case, no, none of these are the difference of two squares. So we're finally done with that problem. The end. So follow your decision tree. Ask yourself these questions as you go. And that's how to factor completely. You have to factor until it will not factor anymore. The end. Go home. Bye.